Okay, so we're going to look at something called hypothesis testing. This is a bit of a funny bit of statistics in which quite often you'll find you'll feel like you're hardly doing any maths at all. Um, there's not actually that much calculation involved. You don't really need to know much about arithmetic or algebra or that sort of thing. It's it's a little bit quote unquote wordy. So hypothesis testing mainly involves you understanding a statistical process and demonstrating that you can understand this, and that's how you'll usually be questioned on it. In terms of exam technique, you should understand hypothesis testing quite well because it tends to be worth a lot of marks and they tend to be quite easy marks. Um, but regarding the concept itself, it can be a little bit tricky for some because um, it's mainly about understanding the concept rather than doing the calculation. So if you're quite used to being very good at calculating various things, you may find you need a little bit more time to get to grips with hypothesis testing. So really do make an effort to try and follow along with the concept as much as possible, because you're not going to be given some magic formula to just plug numbers in. It's about the concept itself. Okay, so to get you into the right mind of thinking about problems relating to hypothesis testing, here is one to start with. And it's not necessarily about calculating a probability. So if I roll a six-sided die 60 times, so a normal die, not necessarily like the one pictured, if I get a 3 15 times, do you think that's reasonable? And I've deliberately used a bit of an ambiguous word here, reasonable. So I leave that up to your interpretation to see what you think about that. Do you think it's reasonable for someone to, I don't know why they would be doing this, but someone walks up to you and says, hey, I just rolled a die 60 times. I got a 3 15 times. What do you think about that? Is that, regardless of how strange the conversation is that a reasonable thing to expect to happen? Okay, so have a think. You could perhaps do a bit of calculation to justify your answer, but pause and have a think. What do you think? Is it reasonable? Okay, so I'm not actually going to say yes or no to this answer, mainly because in order to justify that answer, we need to have understood hypothesis testing. So the point of asking this was to demonstrate why we need hypothesis testing. Hypothesis testing answers questions like this. It answers questions where something has happened and you want to know, has that thing happened because we got lucky, or has it happened because something else is going on? For example, the die is biased, right? Just to demonstrate why I chose the number 15, if I said I got the number 3 10 times, you would say, well, that's not surprising at all. That is in fact about what I would expect. I would expect the number 3 to come up about 10 times out of 60. If I said to you, I rolled it 60 times and I got a 3 60 times, then you would definitely say, no question at all, there's something going on with this die. There's no way you rolled a 3 60 times. So there's clearly a spectrum between, in this case, 10 being that makes complete sense, to 60 being you're either lying or the die is biased or something else is going on. So the question is, where on the spectrum do we define reasonable and unreasonable? And it's not necessarily as simple as you might think. So that is what hypothesis testing is going to answer for us. So throughout this session, I'm mainly going to be introducing terminology. So as I say, it's a bit of a wordy session. We won't do that much calculation, but you do need to understand the terminology, and the questions at the end are mainly going to be testing you. Have you understood the terminology? Okay, so first bit of terminology. The subject is hypothesis testing. what is a hypothesis? So you probably have some idea of what a hypothesis is. It's, in some sense, a kind of guess, or an intelligent guess or an expectation about what is going on in a certain situation. But to just hone it down a little bit, I've given here 3 examples of hypotheses. More than one hypothesis is hypotheses. So we've got 3 hypotheses here, and we're just going to run through them one by one and talk about the key hypothesis testing language. Okay, so the first of these is a hypothesis that a die is biased. Like in the previous example, do we think that the die you were rolling was biased or not? So the first bit of terminology I'm going to introduce is the idea of something called the null hypothesis and the alternative hypothesis. Okay. Your null hypothesis, or H0, and you write it as an H with a little naught on the bottom, is the default position. It's basically the position that disagrees with what you think might be happening. So if you think, I want to check if this die is biased, then the default position is to say, well, by default we assume it's not biased, right? Effectively, by default, everything's fine, everything's normal, everything is as you expect it to be. This is the default position within hypothesis testing. The alternative hypothesis is basically, someone comes along and says, actually, I think it might be something else. Something else is going on here. It's not what you think. This is what we call the H1. Okay? And in this case, we said H0 is the die is, let's just say it's normal. So, or let's be a bit more specific. The die is not biased. I think the normal has too many mathematical connotations. And H1 is the die is biased. Okay. So what we now need to do is to find each of those terms mathematically as well, biased and not biased. The way we do that is we talk about the population parameter. Okay, the population parameter is basically a number which tells you about how this object behaves. Why it's called population parameter is ultimately down to the fact that you're going to be doing something many times. You're going to be rolling this die many times, and every time you roll it, this parameter dictates how it behaves. In this case, our population parameter is going to be the probability that you roll a third, or that you roll a 3. So let's just say, let's call it P. And P is our population parameter, and it's the probability of rolling 3. Okay, and this decides the behavior of the die, at least the specific aspect of the behavior that we're interested in. Okay, perhaps I should have said a hypothesis that a die is biased with regards to rolling 3, just to be specific. That's really what the full scenario is. We care about the 3s. So our population parameter P, by default, what is it? By default, what do you expect that p-value to be? The probability of rolling 3. We expect it to be 1 in 6. So we write H0 colon, or H0 equals P, no, actually not, you wouldn't say equals, you would use colon. So you'd use H0 colon P equals a 6th, and the alternate is H1. What is P going to be? Your alternative is you saying, I don't believe the null hypothesis, I think something else is going on. So you'll write not equal. So equals with a line through it, meaning not equal. So P is equal to anything other than a sixth. I suppose it still has to be between 0 and 1 because it's a probability, but it's not a sixth. Okay? And let me just check that's all the terminology I wanted to talk about for now. Yes, that's it. Okay, so that's our first hypothesis, that a die is biased with respect to rolling threes. Your null hypothesis, H0, is that P equals a sixth, where P is the probability of rolling a 3. Your alternative hypothesis, H1, is that P is not equal to a sixth. H0 is your null hypothesis. H1 is your alternative hypothesis. P, in this case, is the population parameter. Okay, so now we've seen it for the first one, so we should now more easily be able to do it for the other two. So number 2, a hypothesis that the infection rate of a disease has decreased, topical. So we need to think about what the population parameter is. So in this case, what is the population parameter? What is the thing, what is the number that describes the scenario? It is the infection rate, okay? And I've chosen this, I'm going to go with the UK government's particular population parameter they use, which is the R number. So if you've been following that, if the R is bigger than 1, that's bad. If the R is less than 1, that's less bad. So an increase, a high infection rate corresponds to R being greater than 1. A lower infection rate corresponds to R being less than 1. So if you have a hypothesis that is decreased, then you're saying, I think the R is lower than everyone else says it is, right? So I have to make up a few numbers for this to make sense. But let's say the government or the government representatives, they come on television and they say the R is equal to 1.2, right? And everywhere in all the recent published articles, everyone's saying R is equal to 1.2. Therefore, that's the null hypothesis. That's the default position. So we're going to say H0 R equals 1.2. Okay, it depends on the question. It'll be given to you. You'll be told what the null hypothesis is, or it'll be obvious from the context. So let's say by default everyone says it's 1.2. What is your alternate hypothesis? Well, according to the phrasing, it's a hypothesis that the disease that the infection rate has decreased. So in this case, your null hypothesis, sorry, your alternative hypothesis, H1, is R less than 1.2. So rather than not equals, we're just going to use less than. Not equals is for when you don't know if it's gone up or down. Less than is for when you're suspecting, your hypothesis is that it's gone lower. Okay, and that's it. And again, in this case, that infection rate R, this is our population parameter. Okay, let's look at the last one. I think my face has just cut off the last word there. This says a hypothesis that the quantity of sugar in a Coke is more than the packaging states. So you look at, let's say, a can of Coke, and on the Coke it says this Coke contains a certain number of grams of sugar. In fact, let me just look up how many it should be. Okay, so apparently it's 39 grams. So the population parameter is the thing we're interested in, the thing that describes the scenario, and the thing that we're making a hypothesis about is the quantity of sugar. We can call it whatever letter we like. Often we'll use things like P. Let's say it's S. That's the quantity of sugar. The null hypothesis is then what? I just told you the can claims 39, right? So the null hypothesis is that there's 39 grams. That's what the packaging states. It's what everyone believes. So by default, we say it's probably got 39 grams in it. Then you come along and say, well, I want to do a test. I want to check, is that really the case? I think it might be something else. You're going to say then that alternative hypothesis, and in this case, notice the wording more than. It's all about changing the English language into the notation. So in this case, someone believes there's actually more in there. So you're going to write alternate hypothesis H1 colon is S greater than 39. We think it's actually more. Okay, so far we have learned about null hypothesis, alternative hypothesis, and the concept of the population parameter. In addition, you've seen the three, and these are the only three, ways in which the alternative hypothesis is formed. It's either a not equals, or it's a less than, or it's a greater than. That's all you're ever going to see in hypothesis testing. There are no other possibilities. So we've covered all bases there. Okay, so next, keep those three scenarios still in mind. Hopefully you remember what they were. Bias dye, infection rate decreased, Coke can sugar has increased. And with those in mind, we're now going to actually do the test. Okay, so there's two parts to a hypothesis test, the hypothesis and the test. We've looked at the hypothesis, and now this is how we do the test. So to do the test, you need a new bit of terminology, the test statistic. So the test statistic is the thing you're going to do to test if things are as they seem. Right, I'm leaving this as vague as I can because it genuinely can be quite vague. In hypothesis testing, you're quite free to choose your test statistic. So we've got three examples here. The first case, testing if the dye is biased towards threes. If you wanted to check that, a logical thing to do would be, well, roll the die lots of times and see how many threes come up. So that's what we're going to do. So this is one specific example. Count the number of threes in 60 throws. Okay, much like the starter. So it doesn't have to be 60. It could be some other number, but it's just an example. I'm going to throw the die 60 times and count the number of threes. That's a number, right? A specific number. It's going to happen. I roll it 60 times. I'll get a number of threes. That is my test statistic. Okay, so this thing here, number of threes in 60 throws, is my test statistic. In the second case, counting the total number of newly infected over a period of 1 month. Again, that makes sense, right? If you wanted to figure out what is the infection rate currently, well, let's track the population of the country over a period of a month and see how many new infections we have. That will then give us some idea of whether or not our R number is accurate or not. So that's the test, that's the experiment. And again, this number, whatever it may be, is the test statistic. Okay, that number will probably be given to you within the question, but you have to recognize which numbers are what. So in this case, that's the test statistic. And then finally, if I wanted to check, is Coke telling the truth about the amount of sugar in the can? And I'm not claiming it's not, but let's say you wanted to test it. You wanted to hypothesis test it. You would probably just get a whole bunch of Coke cans, measure the sugar quantity, and see what is that number? What am I getting on average, right? So in fact, let's be specific here, measuring the, let's say, average. Okay, so you could get a large number of Coke cans, let's say 10,000, take the average amount of sugar in each, which is a real number, you've calculated it by experiment, that's your test statistic. Okay. Again, that's the test statistic. Okay, so one more bit of terminology to add to our very wordy lesson is test statistic. Okay. So now the good news is out of these three scenarios, only one of them is the type of scenario that we're going to be working with, and that is the first one. And the reason we're going to be working with that type of scenario is because it's described by a binomial distribution. Okay, so now we get on to why we've started talking about hypothesis testing, because we're going to be using it for binomially distributed variables. Okay. So let's start actually looking at some examples, and hopefully this isn't going to be too difficult now, because after all of that explanation, we hopefully know what all these various words mean. Okay, so in the examples coming up, everything's now going to be a binomially distributed scenario. So this person, John, wants to see whether a coin is unbiased or whether it is biased towards coming down heads. Tosses the coin 8 times and counts the number of times x that it lands head uppermost. Describe the test statistic, write down a suitable null hypothesis, write down a suitable alternative hypothesis. Notice we're not being asked to do any calculations. What we are being asked to do is to put down the correct words on paper to demonstrate that we've understood what we're being asked to do. So first off, what is the test statistic? Is it the coin being thrown 8 times? Is it the heads? Is it John? I mean, what is the thing in here that is the test statistic? It is the number which comes as a result of performing some sort of experiment, right? So in this case, our test statistic is x, right? And that is specifically the number of heads in 8 tosses. Okay, that's it, that's the answer, that's the test statistic. Write down a suitable null hypothesis. The null hypothesis is H0 colon. And what is it? By default, what do we assume about the coin? So remember, the null hypothesis is a statement about the population parameter. This question hasn't actually asked us to state the population parameter, so we're going to have to define it ourselves. The suitable population parameter, the thing that describes the behavior of the coin, is the probability of it turning up heads. What is by default the probability of turning up heads? It's a half. So we're going to say P equals a half, and I'm going to write in brackets P is probability of heads coming up. Okay, so that's it. By default, null hypothesis P is a half, and then the alternative, and now we just got to read it quite carefully. He wants to see whether a coin is unbiased or whether it is biased. So there's no sense of him saying it's more likely to get heads or less likely to get heads. It's just, is it different from being biased? And by definition, for a coin to be biased means that it's just not equal to a half, the probability of getting heads. So that's what we're going to put here. Probability is not equal to a half. No, sorry, hang on. I take it back. We've got to be really careful about the wording here. Whether it is biased towards coming down heads. Okay, so his hypothesis is, I think it comes down heads more. So this is something we really got to be aware of, so good thing you saw that mistake. It does actually specify. he says, I think it comes down heads more. It's biased towards coming down heads. So in that case, P greater than a half. Okay, and that's it. Make sure that we do define what the P is. If you just write P by itself, it's not entirely clear. You should define the population parameter. In this case, it's the probability of heads coming up. Okay, so we've got a little bit more terminology, I'm afraid, before we look at the second example, the last example. So the first of these is something called the significance level of a test. This will be usually given to you in the form of a percentage, and examples of a significance level, when you see them on the page, they'll look like things like 1%, 5%, 10%. These are the typical numbers used. So what is a significance level? The significance level is how unlikely something has to be before you change your mind from that was a coincidence to that seems really unlikely, I think something's biased, or it's not as it seems to be. So that's the intuitive understanding. Effectively, by default, you're at the null hypothesis, unless you do a test and something's so unlikely, you think, actually, we need to. I'm going to change it to the alternative hypothesis. So a specific example of that would be the coin, the die. I flip it, I roll it 60 times, and let's say it came up 60 times. Now that's really, really unlikely. In fact, it's less than 1% likely. So if your significance level was, say, 1%, then you would still say, well, that's less than 1% chance of happening. So I'm going to reject the null hypothesis and switch to the alternative hypothesis. Where things get trickier is when it's on the boundary. So let's say I rolled the die 60 times and I got 15 threes. You would then, as part of your hypothesis test, you would calculate what the probability of getting 15 threes is, or even more threes than that. And if that probability is less than 1%, you would change your mind. You would say, I think that's so unlikely, it must be biased. Unless your significance level was 5%, in which case you would say, if it's less than 5% probability, I'm going to change my mind. Effectively, the choice of the significance level is you defining the word reasonable in the sentence, is it reasonable to get 15 heads? So that's what I want you to think of the significance level as. The significance level is it's an attempt to quantify the word reasonable. Because we have to pick a number somewhere. We have to say, what is your boundary between likely and unlikely? Do you say something unlikely is when it happens 5% of the time or 1% of the time? There's no real definition we can come up with that's going to be consistent. So instead, depending on the question you're given, you'll be given a significance level. The question will say 5% significance level. That's what you're testing on. So the important thing is, as part of our hypothesis test, you will already have the significance level before you even start doing anything, before you even start counting sugar in Coke cans or counting infected numbers of people. You already know the significance level that will determine if you go with H0 or if you go with the alternative hypothesis. Okay, the specifics of this we'll look at in an example, but you just need to know what the word significance level mean. It means the percentage which represents the boundary between reasonable and unreasonable, or likely and unlikely. Okay, and final bit of terminology, the words two-tail and the words one-tail. This one's really easy to remember. You saw before, right? We had these three possibilities. P is equal to something, or P is not equal to something. P is less than something, or P is greater than something. Right? These are the three possible forms of your alternative hypothesis. So just remember it as follows. This one we call two-tail. This one and this one we call one-tail. And for now, I'm just going to give you the rules without fully explaining them, because you'll later on, and probably in year 13 as well, you'll get into more detail about why these things are called one-tail and two-tail. I'm just going to give you the rule for now. If it's one-tail, then your significance level I'm trying to think of the best way to phrase this. It just stays the same. Meaning, if the question says 5% significant level, that is the significance level. So in other words, nothing changes. So the only one we need to be aware of is the two-tail case. If your alternative hypothesis is two-tail, then you need to take the significance level you're given and halve it. Just divide it by 2. And that's it. Okay, so that's the terminology and that's the rule. The underlying reason for why we do this, I won't get into now, but it ultimately relates to the fact that if something's not equal, it can be both above or below, 2 possibilities. If something's less than, there's only 1 possibility. And if something's greater than, there's only 1 possibility. I think that's about enough of an explanation as you need at this stage. Let's actually look at an example. See if we can put all of this together now and answer the question. Okay. An election candidate thinks she has the support of 50% of residents in a particular town. So she's walking around town and she thinks 40% of the people she sees on the street are going to vote for her. That's what she thinks. However, a researcher comes along and wants to test this, wants to see, is that really true? I suspect perhaps it isn't. That researcher says, right, my significance level, my definition of reasonable is 5%. If something is less than 5% likely, I deem that as unlikely and I'm willing to then change my opinion. Right, that's the basis on which I'll change my opinion, is if something happens that's less than 5% likely. Right, and the hypothesis is on whether the candidate is overestimating her support. So specifically, this researcher is dubious and thinks, I think that you think you're more popular than you actually are. Right, so it's not that they're saying you're wrong, it's a specific type of wrong. They think that this candidate is overestimating. Actually, less than 40% of people want to support this candidate. Okay, but we don't know. So in order to find out, the researcher asks 20 people, which is not that many people at all, really. So this is a poor test, I'll just point out now. But in a town, you would ask obviously thousands, maybe tens of thousands of people. But this researcher asks 20 people whether they support the candidate or not. And out of those 20, 3 say, yes, I do. So before we look at the question, let's make sure we've understood what's going on and also already think about our expectation. If you said 40% of people support me and then I ask 20 people and only 3 of them say they support you, at that point, you should be thinking that's suspicious, right? You claimed 40%, so 40% of 20 is what? It's about 8. It is 8. So I would expect about 8 people to say they support you. However, only 3 did. So now the question is, did I get unlucky? Did I just pick the wrong 20 people? Or is that so unlikely that I'm actually going to make you change your opinion, it's probably not 40%, it's lower. This is what the hypothesis test is. Okay, so part A, write down a suitable test statistic. So effectively pick out the correct words in this paragraph which align with the test statistic. So what is the number that's being tested, or what is the number which how would I phrase this? What is the number which resulted from the test? It's the 3, right? It's the number of people supporting the candidate. So that's what we write here. Number of people supporting candidate out of 20 specifically. And in this case, the specific value we got for the test statistic was 3. Write down two suitable hypotheses. They're always going to be H0 and H1. So what is the population parameter? What is the thing we're actually testing? It's the level of support. By default, let's just call it P. In this case, population parameter. It's the percentage of people supporting this candidate. By default, it's 40%. Rather than writing it as a percentage, we should write it as just a number. This is the convention. So P is 0.4, right? And what is the alternative? And we've got to be careful here. The researcher says the candidate is overestimating her support, meaning they think it's actually less. Therefore, the alternative is that P is less than 0.4. Okay, and that's it. That's done, the 2 suitable hypotheses. Right, and now C, this is the harder bit, where we have to now bring in significance levels and all that sort of thing. Explain the condition under which the null hypothesis would be rejected. Okay, so we will reject the null hypothesis, and this is a new bit of information that we haven't learned yet. We will reject the null hypothesis if the probability of the test statistic being 3, assuming the null hypothesis is true, is less than 5%. Okay, so I'm going to just write that out in words. The null hypothesis, so that's the H0, is rejected, which means, in other words, we accept the null hypothesis as the alternative hypothesis. So we're going to go with H1. If the probability of 3 or less people supporting the candidate is less than 5%. Under the assumption that H0 is true, assuming P equals 0.4. So this is, a very long statement. I'll be honest, I think you'll understand it more as you start actually applying the null hypothesis, which is what we're going to do in the next session. Okay, so I'm hoping part C is going to make more sense to you as we start to apply it. So I feel like I've talked for quite a while, and that's because I have, and hopefully though at least you have now got to grips with all the terminology. There are a few questions to look at, but they are just about identifying terminology. I don't think they should take that long. So let's take a quick look. Okay, so here are the questions. It was 2 slides. I'm going to just show you the first one because I have talked for a long time. All you have to do in this case is just identify the relevant thing. What is the null hypothesis? What is the alternative? What is the test statistic? Is the situation one tail or two tail? And that's it really. It shouldn't take too long. Just make sure you can identify those things in the wording of the question. And if you can, then hopefully we'll be all set to actually do some maths and some actual applications of hypothesis testing next session. Okay, so give these 3 questions a go, just these 3. You've got a few minutes. Pause the video now.